Welcome back to the Deep Dive. Today, we are not just wading into the shallow end of technology. We are strapping on the heavy gear and going straight into the Mariana Trench of software engineering.
Oh, yeah.
We are tackling the topic that, it usually stands between a senior engineer and that coveted staff engineer title.
Yeah.
It is the final boss of system design interviews.
It really is. It's the one topic where your intuition often betrays you. You can be a brilliant algorithmic thinker. You can know your data structures inside and out. You can reverse a linked list in your sleep. But the moment you introduce concurrency, the moment multiple things happen at the exact same time, the rules of the universe just seem to break.
We are talking about concurrency. We're talking threading, locking, mutexes, race conditions, deadlocks, the stuff that keeps site reliability engineers awake at night, staring at dashboards, wondering why the server CPU is at 100%, but nothing is happening.
Yeah.
And I know for a fact that a lot of our listeners are right now staring down the barrel of a technical interview or a massive architectural review where this is absolutely going to come up.
And the stakes are incredibly high. I mean, if you get a sorting algorithm wrong, your code runs a little slow.
Okay, a half second delay.
Maybe the user waits an extra half second. But if you get concurrency wrong, your bank starts transferring money that doesn't exist. Your inventory system sells the same solitary concert ticket to 5 different people.
Wow.
It's silent, it's often intermittent, which makes it a nightmare to debug, and it is catastrophic.
That's the scary part. It's the silent corruption. It works on your machine, it works in staging, and then it just explodes in production under load.
Exactly.
So our mission today is pretty specific. We have combed through stacks of textbooks, operating system manuals, and high-level engineering blogs. We want to condense that into a single, high-density audio refresher. We want to move past the dictionary definitions, because anyone can memorize a definition and get to the actual intuition. How do you feel your way through a concurrent system design?
Exactly. We want to build a mental model. We're going to use analogies. Chefs in kitchens, bouncers at clubs, people dancing in hallways. Because once you can visualize the movement of data and execution, the code actually becomes the easy part.
Right.
The hard part is seeing the picture.
I love that. So here is the roadmap for the next hour. We're going to start at the bedrock, the definitions. Concurrency versus parallelism, processes versus threads.
The fundamentals.
Then we'll move into the danger zone, the hazards like race conditions, deadlocks, and lesser-known live locks. Then we'll pick up our tools, the primitives like mutexes, semaphores, and condition variables. And finally, we are going to take all those pieces and build real things. Thread pools, concurrent caches, and blocking queues.
It sounds like a lot, but it flows logically. We're really just building a house from the foundation up.
Okay, let's start with the most common mix-up in the industry. Concurrency versus parallelism. I'll be honest, for the first few years of my career, I used these interchangeably.
Everyone does.
I'd say, oh, let's run this in parallel, when I really meant concurrent. But there is a distinct difference, right?
Yeah.
And getting it wrong in an interview is bad news.
It is a huge difference. And yes, in an interview setting, conflating them is an immediate red flag. It tells the interviewer you don't understand the underlying hardware or, the operating system.
Yeah.
Ideally, you should view them as 2 totally different categories. Concurrency is about structure. Parallelism is about execution.
Structure versus execution.
Yeah.
That's the headline. Unpack that for me.
So there is a famous quote by Rob Pike, one of the creators of the Go programming language built specifically for this stuff.
Right.
And he put it perfectly. Concurrency is about dealing with lots of things at once. Parallelism is about doing lots of things at once.
Dealing with versus doing. Okay, let's make that concrete.
Let's use the classic restaurant analogy. Imagine a small hole-in-the-wall diner with a single chef, just one person in the kitchen.
Okay.
That chef puts a burger on the grill. Now, while the burger is searing, do they just stare at it for 5 minutes?
No, of course not. They're doing something else.
No. They turn around and chop some onions, then they pour a drink, then they flip the burger, then they plate the fries.
Right. They are juggling.
Exactly. That chef is dealing with multiple tasks. Cooking, chopping, pouring, but they are physically only doing one thing at any given microsecond.
I see.
If you took a high-speed camera, you'd see them chopping or flipping, never both at the same instant. That is concurrency. It is the art of structuring the work so you can switch between tasks efficiently.
Okay, so the execution is interleaved. It's sequential, But it's structured to handle multiple ongoing tasks effectively.
Exactly. The structure of the work allows for overlap in progress, if not in execution. Now, imagine a massive industrial kitchen with 3 chefs. One is exclusively grilling burgers, one is exclusively chopping onions, one is exclusively pouring drinks. They are all working at the exact same instant.
That's parallelism.
That is parallelism.
So parallelism is strictly a hardware constraint. You physically need the multiple cores or the multiple chefs to achieve it.
Precisely. You can write a concurrent program, one that is structured to manage a download, a UI update, and a database save all at once, and run it on a single core machine from 1995.
Right.
The operating system will switch back and forth so fast it looks simultaneous. That is concurrency without parallelism.
But you can't have it the other way around, right? You can't have parallelism without concurrency.
No, you really can't. To have parallelism, you must have concurrency first. You need to have structured your program into independent tasks. The recipe needs to be broken apart before you can hand those pieces to different cores.
That makes sense.
If your code is one giant linear do step A, then step B, then step C block, having a 64-core machine won't help you at all.
Right, you'll just use one core.
You'll use one core, and the other 63 will sit idle.
That's a crucial distinction. Concurrency is the software design challenge. Parallelism is the hardware capability payoff.
Spot on. And often in system design, we are designing for concurrency so that we can exploit parallelism when it's available.
Let's zoom in a bit further to the units that actually do this work, processes and threads. I think we all have a vague notion that a thread is lighter than a process, but let's get specific on the mental model. Why do we even have both?
Okay, so think of a process as a house.
A house.
A fully self-contained unit. It has 4 walls, that is your memory isolation. It has its own resources, its own plumbing, its own electricity.
Okay.
If the house next door catches fire, meaning if another process on the computer crashes, your house is generally safe. The walls protect you. The operating system ensures that process A cannot mess with the memory of process B.
Okay, so process equals house. Secure, isolated, heavy. What are the threads?
The threads are the people living inside that house.
The roommates.
Exactly, the roommates. They share the same address space, the same living room, the same kitchen, the same bathroom. This makes communication incredibly fast.
Right.
If I'm a thread and I want to pass data to you, another thread in the same process, I don't need to, pick up a phone or send a letter through the postal service. I just put the data on the kitchen table. We share memory.
That sounds convenient. No overhead for communication.
Mm-hmm.
But I imagine that closeness comes with a significant downside.
A massive downside. If one roommate decides to set the kitchen on fire, say a thread triggers a segmentation fault or a fatal error, the whole house burns down. The entire process crashes.
The whole process goes down.
Threads share fate. You cannot isolate a crash to a single thread usually. If the process memory is corrupted, everyone dies.
And what about the cost of creation? We hear processes are expensive, but how expensive are we talking? I mean, in real terms.
It's orders of magnitude. Creating a process involves the operating system setting up a whole new virtual address space, loading page tables, establishing security contexts, allocating file descriptors. It's a lot.
So it's slow.
It takes milliseconds. And in CPU time, where we think in nanoseconds, that is an eternity. It's like building a new house from scratch every time you need one.
And creating a thread.
Creating a thread is microseconds. It's mostly just allocating a bit of stack memory within the existing house. It's like inviting a friend to come over. They just walk in.
This explains why, historically, web servers moved from process per request to thread per request.
Exactly. In the early days, like with CGI scripts, every time you visited a website, the server spawned a new process. If you had 100 users, you had 100 processes.
Right.
If you had 10,000 users, the server would just choke and die. You just run out of memory and CPU cycle setting up all those houses.
And with threads.
If you use threads, you can handle thousands or tens of thousands because they are so much lighter.
However, it is worth noting that processes are kind of gaining popularity again for isolation. I mean, look at Google Chrome.
Right. Every tab in Chrome is a process, or at least they try to be. Why? Because if one tab crashes, if one web page has bad JavaScript, they don't want the whole browser to close.
That's a good trade-off.
They are willing to trade the higher resource costs using more RAM for better stability and security. It's always a trade-off.
Before we leave the foundations, I want to touch on the thread lifecycle. I feel like this is something candidates gloss over, but the OS scheduler is Ruthless. It's not magic.
It is not magic at all. You need to understand that just because you create a thread, it doesn't mean it's running. You start in the new W state. You've just, defined the thread object in your code.
Okay.
Then you call start, and it moves to runnable. This is the waiting room. The thread is ready. It has its running shoes on, but the CPU, the chef, is busy with someone else.
So it sits in a queue waiting its turn.
Ideally a queue, yes. Eventually, the scheduler picks it, and it becomes running. Now it's actually executing instructions on the silicon, but then it might get kicked off.
Because of a context switch.
Right. Or it might block itself. It moves to blocked or waiting. Maybe it tries to read a file from disk. The CPU says, I'm not waiting 10 milliseconds for the hard drive to spin up.
Right. That's an eternity.
So it kicks the thread off the core, puts it in the waiting room, and grabs another thread. This constant swapping context switching is the heartbeat of concurrency.
And context switching isn't free. I think people forget that stopping one thread and starting another has a cost.
Far from it. When you switch threads, you have to save the state of the registers, the program counter, and the stack pointer. But the real cost, the hidden cost, is the cache pollution.
Oh.
The new thread brings in new data, wiping out the hot data in the CPU cache, the L1 and L2 caches. It takes a while for the CPU to get up to full speed again because it has to fetch data from slower RAM.
It's like a chef having to clear the counter and get completely different ingredients for a new dish every 10 seconds.
That is a perfect visual, yes.
Okay, so we have our threads. They're living in this house, sharing the kitchen, and the OS is swapping them in and out of the kitchen rapidly. That chaotic environment leads us directly to the danger zone. Section 2, hazards.
This is where the horror stories come from. This is where the theory meets the painful reality.
Let's start with the big one. Race conditions. We hear the term constantly, but can you give us the definitive definition for an interview?
A race condition happens when the correctness of your system depends on the uncontrollable timing of events. You are racing to get to the finish line, and if the wrong thread wins, or if they tie, the data breaks.
I think the count plus plus example is the classic here. It looks like one line of code. It's count plus one. How can that possibly break?
It looks like one line to you, the programmer, in a high-level language like Java or Python, but the CPU doesn't see one line. The CPU sees 3 distinct operations. 3 steps. First, read. Fetch the current value of count from memory into a local register. Second, modify. Add 1 to that register. And third, write. Store the new value from the register back to memory.
Read, modify, write. And the OS can pause a thread between any of those steps.
Exactly. That is the hazard. Imagine count is 0.
Okay.
Thread A comes along. It reads 0 into its register.
Got it.
Suddenly, context switch. The OS pauses thread A. It hasn't added anything yet. It's just holding the 0.
Okay.
Thread B wakes up. It reads the shared variable. It still sees 0. It adds 1. It writes 1 back to memory. Thread B is done. The global count is now 1.
Okay, so the variable is 1. Now thread A wakes up.
Thread A wakes up, but remember, it has its own registers.
Yep.
And in its register, it still has the value 0 that it read before it went to sleep.
Oh.
And it doesn't know thread B changed anything. So it takes that 0, adds 1 to it, getting 1, and it writes 1 to memory.
So thread B's work is completely obliterated. The count should be 2, but it's 1.
Correct. That is a lost update. And it's terrifying because, like we said, the code didn't crash. It didn't throw an error. It just silently corrupted the data.
And if that count was number of items in stock?
You just sold an item you don't have. If it was bank balance, you just gave someone free money.
There's another type of race condition you mentioned in the notes. Check, then act. This feels more logical, but I guess it's just as dangerous.
Yes. This is so common in initialization logic or security checks. You check a condition if instance null.
Right, the classic singleton pattern.
Then you act. Instance new singleton. If 2 threads check at the same time, they both see null, they both enter the if block, they both create a new instance.
And now you have 2 singletons.
No, you have 2 singletons, which is an oxymoron, or a scarier example, a security check. If user.have_access, by the time you run the sensitive code, the user's access might have been revoked by another thread in that little gap.
So the takeaway is, whenever you have shared state that is mutable, meaning it can change, you are at risk.
Yes. And, immutability is the ultimate cure. If the data can't change, you can't have a race condition. Read-only data is always thread-safe.
But most data isn't read-only.
Right. So if it must change, you must coordinate access. You cannot let the threads run wild.
Before we get to the coordination tools, let's distinguish between 2 ways the system can freeze. Deadlock versus live lock. We all know deadlock, the dining philosophers, everyone's still holding a fork, waiting for the other. But live lock is subtler.
Deadlock is when everyone is waiting. Thread A holds lock 1 and wants lock 2. Thread B holds lock 2 and wants lock 1. Nobody moves. The system just halts.
And CPU usage would drop, right?
Usually it drops to 0 because everyone is sleeping, waiting for a lock that will never be released.
Okay. And live lock.
Live lock is when threads are active, they are running code, they're burning CPU, but they are not making progress. The best analogy is the hallway dance.
No, I hate that. You step left, they step left.
Exactly. You're walking down a hallway, someone is coming the other way, you step to the left to let them pass, they step to their right, which is your left, to let you pass.
Then you're stuck again.
Now you're blocking each other again. So you step right, they step left. You are both moving, you're both expending energy. Your CPU usage is at 100%. But you aren't going anywhere.
You're stuck in a loop of politeness.
That's a great way to put it. You're stuck in a loop of politeness.
That's a great visual.
Right.
In code, this happens with retry logic, right?
Yes. It often happens with overly polite algorithms in distributed systems. You know, oh, the resource is busy, I'll back off and try again. If two threads back off at the exact same time and retry at the exact same time,
They just collide again.
they collide again. This is called resonance. They get into a rhythm of failure.
So how do you solve the hallway dance? How do you break that rhythm?
You introduce randomness. It's called jitter. If you both step left, wait a random amount of time, say, pick a number between 10 meters and 100 meters before moving again.
Ah, so you're not synchronized anymore.
Statistically, one of you will move before the other, breaking the cycle. Ethernet networks use this exact strategy to handle collision detection. It's a proven technique.
Randomness as a feature. I like it. Okay, let's move to section 3. The primitives. These are the building blocks we use to solve these problems. The most basic one, the hammer in our toolbox, is the mutex.
Mutex. It stands for mutual exclusion. It is a lock. And the key rule of a mutex is ownership.
Ownership. Why is that the key word?
Think of a single occupancy restroom in a coffee shop. It has a key attached to a giant spoon so nobody steals it.
Right.
Only one person can hold that key at a time. If you have the key, you are in the restroom. That is the critical section. Everyone else has to wait outside. But crucially, the person who locked the door must be the one to unlock it.
Got it.
You can't have someone else reach in with a coat hanger and unlock it for you. That's ownership. The thread that acquires the lock must be the one to release it.
That protects the critical section so only one thread can modify the shared state. It serializes the access. Now, how is that different from a semaphore? I feel like people mix these up constantly because they both block threads.
They do mix them up. A semaphore is fundamentally different. It's not about ownership. It's about capacity. Think of a semaphore like a nightclub bouncer with a clicker.
Okay, a bouncer.
The bouncer doesn't care who goes in, just how many. Let's say the club capacity is 100. That's a semaphore initialized to 100. Every time someone enters, the bouncer clicks. That's a decrement. Every time someone leaves, they click. That's an increment. If the count hits 0,
The line stops.
the line stops. No one else gets in until someone leaves.
So there's no ownership.
Correct. And this is the vital distinction. Thread A can acquire a permit, enter the club, and thread B can release a permit.
Wait, another thread can release it.
Yes, that's the key. This makes semaphores very powerful for signaling patterns where different threads need to coordinate, rather than just locking data to protect it from other threads.
And there's a specific type called a binary semaphore, right, where the capacity is just one. Is that just in mutex?
It looks like a mutex because online the one thread can proceed, but again, it lacks ownership. Because any thread can release it, you can use it for things a mutex can't do, like an interrupt handler signaling a main thread.
I see.
But for simple locking to protect data, use a mutex. It's safer because the runtime can check for errors like, hey, you're trying to unlock a lock you don't hold.
Got it. Mutex is the bathroom key. Semaphore is the bouncer. Now, let's talk about condition variables. This is the one where I think the intuition is tricky. Why do we need them? Why can't I just check a flag in a loop?
Okay, so imagine you are waiting for a specific condition, like wait until the pizza arrives.
Right.
The naive way to do this is busy waiting. You keep walking to the door, opening it, checking the porch, closing it, walking back, checking again, every few milliseconds.
That's exhausting. And it burns 100% CPU. You're just spinning.
You're spinning. Condition variables allow you to just go to sleep. You say, wake me up when the pizza is here.
Yeah.
You consume 0 resources while waiting. But here's the catch. You need a lock, a mutex, to use a condition variable.
That's the part that always confuses me. If I'm just sleeping, why do I need a lock?
To prevent the lost wake-up problem.
The what?
The lost wake-up.
Yeah.
Imagine you walk to the door to check for pizza. You see it's not there. You turn around to go to the couch to sleep.
Okay.
But in the precise microsecond between you looking at the empty porch and actually falling asleep on the couch, the delivery guy arrives, rings the doorbell, and leaves.
Oh, I missed it.
You didn't hear the ring because you weren't fully asleep listening yet, but you weren't looking at the door anymore either. The signal came, and you missed it. You will sleep forever.
That is the race condition, the gap between check and wait.
Exactly. The mutex protects that sequence. It ensures that the check is pizza here, and the sleep action happen atomically, effectively. When you call wait on a condition variable, the system atomically releases the lock and puts you to sleep. This closes the gap so signals can't slip through.
And there's one more rule with condition variables, right? You always put them in a while loop, not an if statement.
Yes, always.
Wait, and why is that?
This handles spurious wake-ups. Sometimes, purely due to OS implementation details, a thread might wake up even if no one signaled it. It's rare, but it happens.
So it just wakes up for no reason?
Pretty much. And if you use an if statement, you'll wake up, assume the pizza's there, try to eat it, and realize you are eating air. You must check the condition again after waking up, just in case.
Always wait in a while loop. I'm tattooing that on my arm. Okay, let's level up. Section 4, advanced locking strategies. Sometimes a standard lock isn't enough. What happens if I write a recursive function, a function that calls itself and it needs to grab a lock?
If you use a standard non-reentrant lock, you will deadlock yourself instantly.
Right.
Function A grabs the lock. Function A calls function A recursively. The inner call tries to grab the lock. The lock says, sorry, someone already has this.
And the lock doesn't know that this someone is actually you.
Exactly. The lock is dumb. It just sees locked. It doesn't check ID. So we use a reentrant lock. Think of this like a hotel key card. Once you check in, acquire the lock, you can re-enter your room as many times as you want. The lock tracks the owner thread and a hold count.
A hold count.
So the first lock sets the count to 1. The recursive call increments it to 2. When you exit the inner function, it decrements to 1. When you exit the outer function, it hits 0, and then the lock is released for others.
That solves the recursion problem neatly. What about the reader-writer problem? I've used this for caches before, and it feels like a big win.
This is a classic optimization. In many systems, like a cache or a configuration setting, you read the data way more often than you change it.
Right, like a 99-to-1 ratio.
Exactly. A standard mutex treats reads and writes the same, only one person at a time. But reading is non-destructive. 10 people can read the same book page simultaneously without any issues.
So the reader-writer lock allows multiple readers.
Yes, it allows shared access for readers. Infinite readers can jump in as long as nobody is writing. But the moment a writer shows up, they need exclusive access. No readers, no other writers.
So it's a mutex for the writer.
It acts like a mutex for the writer, but like an open door for readers.
Is there a catch?
There is always a catch. It's called starvation.
Starvation.
Imagine you have a popular book. Readers are constantly picking it up. A librarian, the writer, wants to update a page, but every time they look, someone is reading. New readers keep arriving before the old ones finish. The writer never gets a turn because the lock is never fully free.
Writer starvation. The update never happens because the readers are too aggressive.
Right. So good reader-writer locks implement fairness policies. If a writer is waiting, the lock will block new readers from entering until the writer has had their turn.
Oh, I see.
It clears the room so the writer can work. It sacrifices a bit of throughput for correctness.
Interesting. So it's a balancing act between throughput, which is letting everyone read, and fairness, letting the writer write. One last advanced strategy before we get to patterns. Try lock.
This is for the impatient thread. Standard locks are blocking. If I want the lock, I wait forever until I get it. Try lock is different. It says, I'd like this lock. Is it free? No. Okay, never mind. I'll go do something else. It returns immediately.
This is huge for avoiding deadlocks.
Huge. Remember the deadlock where thread A wants lock B and B wants A? If thread A uses try lock on B and fails, it can say, uh-oh, potential deadlock. I'll release my own lock A, wait a random amount of time, and try again.
It lets the system recover.
It allows the system to recover gracefully instead of freezing.
And it adds responsiveness. You can tell the user, system busy, try again, instead of just spinning the wheel of death.
Exactly. In a banking system, if you try to lock 2 accounts for a transfer and one is busy, you don't want to hang the server. You just fail the transaction and tell the user to retry.
Okay, we have our primitives, we have our advanced locks. Now let's build some things. Section 5, concurrency design patterns. These are the recipes using the ingredients we just discussed.
Right.
Let's start with the signaling pattern using semaphores. You mentioned this earlier, initializing a semaphore to 0. That seems counterintuitive.
Yes. This is a very specific but really useful pattern. Imagine thread A needs to finish some initialization, like loading a massive config file from S3 before thread B can start processing requests.
Okay, a startup dependency.
Exactly. You create a semaphore with 0 permits, thread B starts up and immediately calls acquire. Since there are 0 permits, it blocks. It just goes to sleep.
It's waiting.
Thread A does its work. When it's finally done, it calls release. That creates 1 permit. Thread B wakes up, grabs the permit, and goes.
Why not use a mutex for this?
Because the releaser, thread A, is different from the acquirer, thread B.
Mm-hmm.
Remember, mutexes require ownership. A mutex would throw an error if thread A tried to unlock a lock it didn't hold.
Ah, right. And why not use a condition variable?
You could, but semaphores have a memory. If thread A finishes before thread B even gets to the acquire call, the permit is sitting there waiting.
So it's a remember.
Right. Thread B calls acquire and swoops right in without waiting at all. If you used a condition variable and signaled before thread B started waiting, that signal is lost. Thread B would wait forever. The persistence of the semaphore permit makes it safer for this simple kind of signaling.
That persistence is a key feature. Okay, next pattern, producer-consumer. This is everywhere. Message queues, log processing, job pipelines.
The bakery analogy works best here. You have producers, the bakers, making cakes. You have consumers, the customers, buying cakes. And in the middle, you have a shelf. That's the bounded buffer.
And the bounded part, meaning the shelf has a limit, is critical.
It is absolutely critical. If you have infinite shelf space, and the bakers are faster than the customers, you will eventually fill the entire bakery with cakes until it explodes.
That's an out-of-memory error?
That's an out-of-memory error.
Yeah.
You see this in systems where a fast producer floods a slow consumer, so you need a limit. If the shelf is full, the baker must stop. They block. This is called back pressure.
Makes a signal.
It tells the system, whoa, slow down, we can't eat this fast.
And if the shelf is empty?
The consumer must wait. You can't buy a cake that doesn't exist.
So implementing this usually requires 2 signals. One for space available and one for item available.
Exactly. You often see 2 condition variables, not full and not empty. The baker waits on not full. The customer waits on not empty. It's a delicate dance of coordination.
Moving on to the thread pool pattern.
Yeah.
We talked about how creating threads is expensive. This is the solution.
Reuse. Don't fire the chef after every single order. Keep a team of 5 chefs. You have a task queue holding the orders. The chefs, the worker threads, sit in a loop. Is there an order? Yes. Cook it. No. Wait.
The interesting part of thread pools for interviews is the rejection policy.
Yeah.
What happens if the queue is full and all chefs are busy? You can't just keep accepting orders, right?
Right. You have choices, and they define your system's reliability. First, abort. Throw an exception. System overloaded. Harsh but safe. The user gets a 503 error.
Okay.
Second, discard. Just drop the request. Sorry, I didn't hear you. Okay, for logging, maybe you can miss 1 log line. Terrible for payments.
Definitely.
And third, my favorite, color runs. You tell the person who submitted the task, hey, we're busy. You cook it yourself.
So the main thread, the one handling the incoming HTTP request, instead of handing off the work, has to execute the task right there.
Yes, and here is the magic. While it's executing that task, it can't submit any new tasks. It can't accept new connections from the network.
So it naturally throttles the input.
It's a very elegant back pressure mechanism that propagates the load back to the source. It slows down the flood right at the gate.
That is brilliant. It stops the flood at the gate rather than letting it pile up in memory.
Exactly. It saves the system from crashing under load.
Okay, we are entering the final stretch. Section 6, Deep Dive System Design. This is where we apply everything to build real components. If you are in an interview, this is where you earn your paycheck. Let's talk about locking granularity. This comes up when you're designing something like a thread-safe hash map.
Right. Imagine a hash map serving thousands of requests per second. Option 1, coarse-grained locking. You have one big lock for the entire map.
Yeah.
Synchronized map.
Simple to implement.
Simple. Yes. Correct. Yes. Performance. Terrible.
Because if I'm updating key A and you're reading key Z to totally different data points, you still have to wait for me.
Exactly. It effectively turns your fancy multi-core server into a single-core machine for that map. It serializes everything. It's a massive bottleneck.
So what's the alternative?
Option 2, fine-grained locking. You lock every single bucket independently. Great for parallelism, but the overhead of managing millions of locks kills your memory and CPU. Creating millions of mutexes is not free.
So what's the middle ground?
Lock striping. This is what concurrent hash map uses in Java. Instead of one lock or a million locks, you use, say, 16 locks.
16.
Just 16. Lock 1 protects bucket 015, lock 2 protects 1631, and so on. It dramatically reduces the probability of contention. Two threads are only blocked if they happen to hit the same stripe or segment of the map.
That's a great trade-off. You get 16x concurrency with very little overhead. Next, system design challenge. A thread-safe blocking queue. If I ask you to code array blocking queue in an interview, what's the trap?
The trap is using just one lock. If you use a single lock for the whole queue, then enqueuing, adding to the tail, blocks dequeuing, removing from the head.
Even though they're at opposite ends of the array.
Exactly. Logically, adding to the tail and removing from the head are touching different parts of the memory. They should be parallel.
So you use the two-lock algorithm.
Yes. A put lock for the tail and a take lock for the head. This gets tricky, though. You have a shared count variable in the middle. If I add an item, I increment count. If you take an item, you decrement count. Since both threads touch count, you need to handle that safely, usually with an atomic integer.
And you have to be very careful about signaling.
Very. If I add an item to an empty queue, I need to signal the other lock's condition, the take lock's condition, to wake up waiting consumers. It's complex code, easy to get wrong, but it can double your throughput because producers and consumers don't block each other. It separates the concerns.
High risk, high reward. Final design challenge, and this is a classic. A thread-safe cache with TTL, time to live.
Yeah.
We want to store items, but they expire after 10 minutes. How do we implement this safely?
The naive approach is lazy cleanup. When you read an item, you check the timestamp. If it's expired, you delete it and return null.
Seems reasonable.
The problem is the race condition known as TOPT2 time of check to time of use.
Walk us through that race.
Okay. Thread A reads the entry. It checks the expiry. It's valid. It has 1 second left.
There, check is done.
Context switch.
So,
Thread B, maybe it's a background cleanup thread, comes in and deletes the entry because it thinks it's expired, or maybe to free up space, the entry is gone. Thread A wakes up. It holds a reference to the entry, but the entry is gone from the map. Or worse, Thread A assumes the value is valid and performs a calculation, but the data is now stale or inconsistent with the current state of the database.
so how do we fix it? What's the right way?
Two things. First, immutability. The cache entry object, the thing holding the value and the expiry time, should be immutable. Once you grab a reference to it, that object won't change under your feet. Even if it's removed from the map, your local reference is safe.
Okay, that's one part.
Second, atomic compute. If you are doing cleanup, you use atomic operations like map.compute, or even better, map.remove, key expected value.
Remove key expected value. So you say, only remove this key IF, the value is still this specific expired object I saw.
Exactly. If another thread came in and updated the cache with a fresh value while you were paused, the values won't match and the remove will fail. You don't accidentally delete fresh data because you were looking at old data.
That is the kind of detail that gets you the strong hire. It shows you're thinking about the gaps between the instructions.
It's all about the gaps.
We have covered a massive amount of ground today. From the kitchen chefs to the nightclub bouncers to the intricate dance of concurrent caches. If you had to leave our listeners with one final thought, one heuristic for their interviews, what would it be?
Start course, optimize later. When you are asked to design a concurrent system, don't immediately jump to lock-free structures or complex two-lock queues. Start with a coarse-grained lock. Explain why it's a bottleneck. Then apply lock striping or reader-writer locks to solve that specific bottleneck.
So you're showing your thought process.
You're showing the interviewer you understand the trade-off between complexity and performance. Correctness is always more important than raw speed. A slow correct system is better than a fast broken one.
A slow correct system is better than a fast broken one. Words to live by. And for our listeners, try to visualize these patterns next time you're coding. See the semaphore permits flying around. Watch the threads line up for the mutex. It makes the logic much less abstract.
It really does.
Thank you for joining us on this deep dive into concurrency. Good luck with those interviews, and we will see you next time.
Happy coding.